We're going to look at some examples of finding maxima, minima and points of inflection for functions. So we'll be looking at exercise sheet 4 and we start with question 1 part 2. So here we have y is equal to 4 minus 3x minus 2x squared. And we need any local maxima, local minima or points of inflection. So the first step is to look for stationary points. And to find stationary points, I get the derivative and I let it equal to 0. So the derivative there is minus 3 minus 4x. To find stationary points, we let dy dx equal to 0. So minus 3 minus 4x is equal to 0. And we solve that for x. Minus 4x is equal to 3. X is equal to minus 3 over 4. So there is a stationary point at x is equal to minus 3 over 4. We want to know now if that stationary point is a local maximum, a local minimum, or a stationary point of inflection. We do that using the second derivative test. So we get the second derivative. d2y dx squared is equal to, the first derivative is 3 minus 4x, so we differentiate that again to get minus 4. So the second derivative of this function is a constant and it's negative everywhere. So in particular, it's negative at x equal to minus 3 over 4. Less than 0 at x is equal to minus 3 over 4. Because it's less than 0 everywhere. So at this point, x is equal to minus 3 over 4. Let's get y. Y would be equal to 4 times minus 3 over 4. Minus 2 times minus 3 over 4 to be squared is equal to 7 over 4. So at the end we have, what is in here? At the point, minus 3 over 4, 7 over 4, that's the xy coordinates. We have dy dx is equal to 0. And the second derivative, d2y dx squared, is less than 0, or negative. So that means that we have, at that point, a local maximum. Remember that a local maximum looks like this on the xy graph. So the first derivative is positive here, 0 here, and negative here. So if the first derivative goes positive, 0, negative, then the rate of change of that thing must be overall negative. So a negative second derivative is what you get at a local maximum. So we got our point where dy dx was 0, and then we check and we find that the second derivative is negative, which means that that particular stationary point must be a local maximum. We also know that there are no other stationary points, because when we looked, we only found x equal to minus 3 over 4. That's the only value of x where you get dy dx equal to 0. It's the only stationary point. So we found that to be a local maximum. There are no other stationary points, so there is no local minimum or point of inflection. Since there's no other stationary point, there cannot be somewhere where the function turns around to come up again. And so that must actually be the global maximum for that function, because it can't have a higher value anywhere else, because it can't turn around to come back up anywhere else, because there are no other stationary points. Next example is part 3 of question 1. We're given this function, y is x cubed plus 3x squared minus 9x plus 5. So the first step is to look for stationary points. So we get dy dx is equal to 3x squared plus 6x minus 9. As before, we find stationary points by letting dy dx equal to 0. So that means that 3x squared plus 6x minus 9 is equal to 0. So we want to solve that for x to find our stationary points. So the first thing we can do is divide both sides of that equation by 3, and we get x squared plus 2 minus 3 is equal to 0. Then we'll try and factorize this. Sorry, that's 2x actually. factorize this. So we have minus 3 and 2. So x plus 3 and x minus 1. We'll do that. So I factorize that there. If I multiply that out, I get back the previous equation. So I have the product of those two things is 0. So if either one of those is 0, that's a solution. So I can have x plus 3 is equal to 0 or x minus 1 is equal to 0. So that means that x is equal to minus 3 or x is equal to 1. So those are my two stationary points. Let's get my y values there. So x is equal to minus 3 implies that y is equal to minus 3 cubed plus 3 times minus 3 squared minus 9 times minus 3 plus 5, which is equal to minus 27 plus 27 plus 27 plus 5 is equal to 32. And if x is equal to 1, that implies that y is equal to 1 cubed plus 3 times 1 squared minus 9 times 1 plus 5, which is equal to 0. So my stationary points are minus 3, 32, and 1, 0. Now we do our second derivative test to find out what kind of stationary points they are. So we have dy dx already. So the second derivative, d2y dx squared, will be equal to 6x plus 6. Now we can check our two stationary points. Those points are at x is equal to minus 3 and x is equal to 1. So at x equal to minus 3, we have that second derivative is equal to 6 times minus 3 plus 6 is equal to minus 12. So that's less than 0. So that's going to be a local maximum. At x is equal to 1, the second derivative is equal to 6 times 1 plus 6 is equal to 12. So that's greater than 0. So that's going to be a local minimum. And since I only have two stationary points, that's all of the maxima, minima and points of inflection. So I have a local max at the point minus 3, 32, and I have a local min at the point 1, 0. There are no other stationary points, so there are no other local maxima, minima or points of inflection. So if I were to just plot this out, x and y, I have a local max at the point minus 3, 32. So let's say that's here. Let's say this was 32 here on the y-axis. We would have a local max up there, and at the point 1, 0, we'd have a local min right here. So that one on the left there is a max, and the one on the right is a min. So I know, roughly speaking, my function is going to look something like that. Now, I don't know what, we could also work out the y-intercept here to figure out exactly where it crosses. But broadly speaking, it's going to look vaguely that kind of shape, with the max here and the min here. So on this one, if you were to ask what is the absolute maximum or the absolute minimum, well, there isn't one, because this function here will just keep on going up here on the right and keep on going down here on the left. So I have a local max and a local min, but I don't have a global maximum or a global minimum for this function.